Introduction to Systems, Part 2. Causality. A continuous time system S is called causal if, whenever the input xt is equal to 0 and there are no initial conditions, the output is yt is equal to 0. The output yt does not depend on future inputs, but instead it only depends on the present and also the past. So for a value tau is more than 0 when considering causality, it is helpful to think of the time t at which the time the output yt is being computed as the present. So t minus tau would be the past and t plus tau would be the future. Present output depends only on the past and present inputs, not on future inputs. So any practical real-time system must be causal, because real-time system would depend on the present and the past excitation. The response of a causal system occurs only during or after the time in which the excitation is applied. So the response depends only on the present or past. The response of non-causal system, on the other hand, depends on one or more future excitation. So a system is causal if the output depends on current and previous inputs or previous output. When a system works in a time domain, causality is generally required. So we have two equations here, the first equation and the second one. Can you have a guess which one is causal and which one is non-causal? So the first equation is a causal system, while the second one is a non-causal system. So how do you determine this? So in causal system over here, the first equation, the output is only depending on the present and also the past. So t minus 1 and t minus 2 over here is indicating that this output is depending on the past excitation. Whereas for the second equation here, it is denoted as non-causal because there is an element of future over here, t plus 1. So the output is depending on future excitation, even though there is a present and also a past excitation over here. But if you see any plus t plus something over here, that will be non-causal. Next, we have continuous time and discrete time system. So a continuous time system is when the inputs and outputs are continuous time signal. So you have a continuous signal over here, whereas a discrete time system is when the inputs and outputs are discrete time signals. It only occurs at specific time. So discrete time system process data samples, normally regular sampling of t. So usually the continuous time input is denoted as xt, while the continuous time output is denoted by yt. For discrete time, the input is usually denoted by xn, while the output is denoted by yn. So you can actually change from continuous time to discrete time or vice versa. So as you can see from this diagram over here, you have the xt in continuous time. It goes into a system which is continuous to discrete. So that's why you will get the output as Xn in terms of discrete time. And then it goes into another system, which is a discrete time system, which will produce you an output. So that's why you will have Yn over here. So this would be your output in discrete time. Now you want to change back the discrete signal into continuous time signal. So it goes into a system discrete to continuous. And finally, it will produce you an output of Yt, which will be in terms of continuous time signal. So moreover, you have an incoming signal Xt for continuous time. So here you have a continuous signal going into a system H, and it will produce you an output which is still in continuous time. So that's why you have Yt over here, and the signal is in continuous time. So for a discrete time system, whenever you see Xn over here, that means that this is a discrete time signal coming into a system which is discrete time system, and it will produce you an output of Yn, which is also in discrete time. Next, we have the analog and digital system. So analog system is when the inputs and outputs are analog signals, whereas digital system is when the inputs and outputs are in digital signals. So usually digital is denoted by binary numbers 1, 0, 1, 0. Next, we have the invertible and non-invertible system. So an invertible system, if we can obtain the input Xt back from the corresponding output Yt by some operation. So if you have an incoming signal Xt going into a system, and then it will produce you an output of Yt. Next, you have the Yt going into another system, which is a system inverse, and you will get the output as Xt, which is the same as your first incoming signal Xt. So when you have this kind of system, we call it as invertible system. So let a system S produce Yt with input Xt. If there exists another system Si which produces Xt from Yt, then S is invertible. So there should be a one-to-one mapping between the input and also the output. So for example, if you have S, the system is an amplifier with gain G. So it is invertible, and Si is an attenuator with gain 1 over G. So you are going to call the system as invertible only if you have an attenuator system over here that have a gain of 1 over G. So then only you will get back the exact incoming signal. Finally, we have the stable and unstable system. So stability can be internal or external. If every bounded input applied at the input terminal results in a bounded output, the system is said to be stable externally. So this type of stability is also known as BIBO, bounded input and bounded output. So a system is bibostable if the response is bounded when the excitation is bounded by minus infinity up until infinity, provided that your Xt is less than infinity and your Yt is less than infinity. Intuitively, a stable system is one that will remain at rest unless excited by an external source, and will return to rest if all excitation are removed.